Hello, my name is Roy Simpson. I'm an instructor of mathematics at Columbus River College, and we are in the middle of, or actually at the end of, a lecture on equations of lines. In this part, we're just going to talk about finding the equation of a line from its graph. And in this instance, I'm not going to just use a basic, like a graph of a line or something like that. We'll use applications here because that's more entertaining. And we're going to start this off with an example from a textbook. This is from, just for copyright purposes, I should probably say it. This is from the textbook Modeling Graphs and Functions by the Yoshiwaras, Bruce and Catherine Yoshiwara, the third edition for intermediate algebra. Anyway, so what we're going to do is we're going to find an equation for this. So find an equation. And we'll state the slope as well and kind of state the significance of the slope and the intercept. So I'll write that down. So here we go. This figure, by the way, shows the altitude of a skier so many minutes after getting on a ski lift. So 2 minutes after getting on a ski lift, they're at 400 feet in altitude. 4 minutes after getting on the ski lift, they're at 700 feet in altitude. Let's find an equation, and I see 2 points that are nicely labeled on here, or at least nicely kind of highlighted. One of the points is 0, 100. The other point is, let's see, 4, 700. That was actually the point that I just mentioned. So let's go ahead and find the slope. The slope in this situation is just the difference in y values. So I'll take, I've been kind of going back and forth throughout this lecture on finding the slope and which point do I pick. I will tell you right now, from this point forward, I usually pick the first point to write down here is the one with the larger x value. That's the one that's the way I usually do it. So this 4 is larger x value, so therefore I'll go 4 minus 0 on the bottom, and then 700 minus 100 on the top. So make sure the y values are on top, the x values are on the bottom, and make sure that these link up. 704, make sure those are in the same point, and 100, make sure those are in the same point. If they are, then you should be okay. 700 by minus 100 is 600 over 4, which is 150 when you do the mathematics behind the scenes. So we see that the slope is 150, and then again, we don't have to use the point slope form, even though we have a couple points. The fact is, they actually gave us a y-intercept here. But more important still, and in fact, in this case, it's not a y-axis, it's an a-axis, so they gave me the a-intercept. But more importantly, if I hadn't known that they gave me a vertical intercept, I could still use the slope-intercept form of an equation, or of a line. Remember, that's y equals mx plus b, where x is my input variable and y is my output variable. So in this case, my output variable is actually a, and my input variable is t. Sometimes it can be a little confusing when you mix up letters like this, but for now I think we're okay. We know the slope, which is m, is going to be 150. And b represents the vertical intercept, which is 100. And now you see I have my whole entire equation here. Very fast, very fast. And now let's go ahead and state the significance of the slope. As I mentioned in a previous lecture, the one on slope, if you write the units for the axes right next to the letter, so a is in feet and t is in minutes, if you do that, then the meaning of the slope kind of jumps out at you. The meaning of the slope is that you have 150, let's see, rise over run, so the rise variable is in feet, and the run variable is in minutes. So 150 feet per minute, and that's basically that you're rising up 150 feet per minute on that ski lift. Now the significance of the vertical intercept, or what I had written there was y-intercept, but I just changed it to the vertical intercept because there is no y in this whole situation. This is the next thing we need to know. And actually, that's pretty okay too, because the vertical intercept occurs at 100. And it essentially means that when t is 0, a is 100. But that's not enough. You need more than that. What is t? Well, t is the number of minutes that you're on the ski lift. So in other words, when you haven't even spent a single minute on the ski lift, or in other words, when you haven't even got onto the ski lift, the elevation is 100 feet. So basically, elevation at the beginning is 100 feet. And that's a pretty good interpretation. Obviously, you could be more wordy with that if you wanted to, but that's always a good thing to do, is just kind of think about what these problems represent, try to put them in real terms. There's a lot of things you could do here, but that's how you get the equation of a line given the graph. Now there's one other problem I want to do here, and it's not that we're going to be given a graph, but we're going to be given a table in this next problem. And after we're given a table, we could make a graph. I'm likely not going to, but you could, and we'll create an equation for this situation. Now this problem is again brought to you by Bruce and Kathy Yoshiwara from their textbook Modeling Functions and Graphs, Algebra for College Students, 3rd edition. This is a really neat problem about the conversion between gas marks and degrees, gas marks being oven cooking temperatures measured in England. So in England, oven cooking temperatures are often given as gas marks rather than degrees Fahrenheit. The table shows the equivalent oven temperatures for various gas marks. So 3 gas marks is 325 degrees, and so on and so forth. Plot the data and draw a line through the data points. Now, what's kind of vague about that statement is that it doesn't tell you which of these two items is going to be a vertical variable and which of these is going to be a horizontal variable. So I'm actually kind of looking ahead here, and I see that this last question says find an equation that gives the temperature in degrees Fahrenheit in terms of gas marks. When you see that in terms of, that means that what happened before it was the vertical variable, or what we often call the dependent variable. And what comes after it is the horizontal variable, or what we often call the independent variable. And by the way, these ideas of dependent and independent rely upon something more advanced that we'll talk about later on. But I'll just keep mentioning it through my lectures here. So I'll go ahead on the horizontal axis and graph the gas marks, and in the vertical axis I'll graph the degrees Fahrenheit. Now this is going to be somewhat of a challenge just because I'm going to have to freehand draw this, but shouldn't be too horrible. There's a pretty straight line. The faster you go, the better it is, actually. Okay, and we said that the gas marks will be on the horizontal axis. Let's see if they gave me a variable here. No, they didn't. So I bet you a good variable for gas marks would be G, and a good variable for temperature in degrees Fahrenheit would be F. And now I'm going to go ahead and plot some points on here. Now I went ahead and drew this really quickly, and I want to mention a few things before I move on and into the problem and complete it. One of the things I want to mention is the fact that I want you to notice the scale on the horizontal axis. It's pretty customary. It's just a 1, 2, 3, 4, 5, 6, 7, 8, 9. But the scale on the vertical axis has been adjusted. There's a little break in it because I didn't want to sit here and go, okay, 25, 50, 75. I don't have enough paper. So I create this little break right here. Usually looks like a little squiggly line, meaning that somebody just squished that down like a slinky or something like that. Just broke it and squished it down, and they start 325 at a lower level because that's the first data point we really have, is when G is 3, F is 325. So I just wanted to mention that. Otherwise, I kept the scale pretty nice and uniform here. These are in steps of 25. Okay. So the first goal has been completed. We've plotted the data points and drew a line through them. Okay. Now let's go ahead and calculate the slope of this line. And I don't even need to look at the line for that because I have my points right here. I'm just going to grab two of them. Let's see, let's grab the one that says 3, 325 and 5, 375. Now one thing I wanted you to notice, I didn't mention it, but one thing that you probably should have noticed is that all these points do actually exist on a line. So the slope in this case, again, I'm going to pick the one with the higher x value to be first, so 5 and 375. Remember the y value goes up top, or sorry, the output variable goes up top. And then let's see, 3 and 325. 375 minus 325 is 50. 5 minus 3 is 2, which comes out to be 25. The slope of our equation is 25. And in fact, let's talk about the meaning of the slope. It's 25 what? Well, let's go to the graph and ask ourselves that question. The units for the vertical axis are degrees Fahrenheit, and these are just gas marks. I mean, that's what the units are here, just gas marks. They didn't really give us any type of happy unit. So rise over run tells me 25 degrees Fahrenheit per gas mark, which should make sense. Every time I increase by 25 degrees Fahrenheit, I get another gas mark. So if I increase by two sets of them, two sets of 25, in other words, if I increase by 50 degrees, I have also increased by two gas marks. Okay. It says estimate the y-intercept of the graph. It says from the graph. And it shouldn't be y here. It should be the a-intercept. Or not a, I'm sorry. The f-intercept. From the graph, that's actually a bad idea. If I look at this graph, if I'm going to estimate from the graph here, I might get a wrong value. In fact, I will. It looks like it'll just hit right here at 0, 0. But it's not true because remember, I broke this y-axis. So in reality, it's probably better to compute the vertical intercept than it is to just guess it. So we'll write an equation for this and figure out the exact vertical intercept. Now remember, our output variables in degrees Fahrenheit, our input variables gas marks. So I'm taking on the form y equals mx plus b, but we don't have x for an input variable, we have g, and we don't have y for the output variable, we have f. Okay. And I happen to know that the slope here is 25. And now all I need to do is take any of these points and plug it in, and I'll find out what the vertical intercept is. I'll just take this first point here. So I'll let g be 3. And degrees Fahrenheit is 325. That's 75 on the right hand side. I'll subtract from both sides and I get 250 here. So B is 250. In other words, the equation of our line is F equals 25G plus 250. And the vertical intercept here will be 250. What does that mean? Well, it means that at zero gas marks is the same thing as 250 degrees Fahrenheit. And if you think about that, anything below 250 degrees, you're not really cooking things, you're just keeping them really warm. Well, maybe you are cooking them. Who knows? I'm not a cook. So the part C here says, at what temperature in degrees will the gas marks be? This is my hint to myself to make a problem. So I'll say, what degree temperature will yield a gas mark of, I don't know, let's say 6. Okay. So in other words, I want G to be 6, and I want you to figure out what I want the gas marks to be 6, and I want you to figure out what the degree Fahrenheit is for that. Well, let me get a clean piece of paper here. I know Fahrenheit is equal to 25 G plus 250. If I'm going to let G equal 6, in other words 6 gas marks, that's just plugging that in. 6 sets of 25 is 150. Add that to 250 and that's 400. 400 degrees Fahrenheit. So that's how you would do a problem like that. 400. And actually that makes sense too, because if you look at the graph, if I were to go to the graph here, which I think is right here, if I go to the graph and look at G equals 6, or in other words 6 gas marks, you go up here and you see, yep, that looks like it's about at a height of 400. That makes sense. Let's see what the other sub-problems are here. If the temperature increases from 375 to 525, what is the change in gas marks? Okay, that's a fair question. Well, I know that there's a couple ways you could do this. You could do a mathy way, or you could do some logic. I know that for every increase of 25 degrees Fahrenheit, it increases by 1 gas mark. So really what I'm asking is, how many sets of 25 does it increase by when it goes from 375 to 525? So let's go ahead and just get to that sheet of paper here. We want to get to 525 and we're starting at 375. I'll just do that subtraction to see how many degrees we've increased. And that's 150 degree. That's 150 degree increase. Now the question is, how many sets of 25 go in there? In other words, how many times does 25 go into 150? The answer there is 6. So it increases by 6 gas marks. Okay, that's one way you could do it. There's actually several ways you could do that problem, but it is 6 gas marks that increases by. And finally, find an equation that gives temperature in degrees Fahrenheit in terms of gas marks. And we actually have done that. That was the first thing I did. I like to find equations first. So, and you could ask a lot of questions, by the way. If the Fahrenheit is 300 degrees, what are the gas marks? That type of thing.